All right, advanced math A, here we go. We have got rational and irrational numbers. So we're going to be talking about real numbers, and because there's such a thing as imaginary numbers. So real numbers are numbers that show up on the number line. You got a number line. If you got a real number, you can point somewhere on that number line to where that number is. It still might be a decimal, but you can find it on a number line. There's a whole other set of numbers that are called imaginary numbers, and they don't show up on the number line. You'll get to that in another course. But throughout school that you've been in, if you're in 8th grade now, you have dealt with all through elementary school with stuff called rational numbers. Okay, and as you have progressed through math, we've started to introduce irrational numbers. Now, a rational number is any number that can be written as a fraction. When you start off in elementary school, you start off with like 5 and the counting numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are all rational numbers. They can be written as fractions. We usually start when we're teaching kids to start with integers. Integers are positive and negative whole numbers. Now these are rational because they can be written as fractions. So an integer like 17. We can always make this 17 over 1. And so it can be written as a fraction, therefore it's a rational number. The word rational in it, the first part is ratio. Ratio means fraction. All right? I mean, it doesn't actually mean literally a fraction, but basically it denotes it's going to be a fraction. So negative 5 can also be written as a fraction because it can write it as negative 5 over 1. So those are rational numbers. So our integers, which are positive and negative whole numbers, you can always just put them over 1, and that proves that it is a rational number. Next thing we got here is terminating decimals. You probably started these around, like 5th or 6th grade or something like that, maybe even 4th grade, who knows. So terminating decimals are decimals that stop, basically, that end. It's like 7.5. We can turn that into a fraction because this is the 10th place, which means we can change this to be 75 over 10 because it's the 10th place. So then we can reduce that one. It looks like, 5 would go into both of those? 5 would go into 75 15 times? Yep. And then 5 goes into 10 2 times. So 7.5, or we can write that as 15 over 2. And then over here, our terminating decimal, it terminates at the 1000th place. So to rewrite this one as a fraction, we'd put 52 over 1,000. And then let's see, 4 goes into both of those, I think. Yeah, 4 goes into 52 13 times. 4 times 13, yep. And then 4 goes into 1,250 times. So 0.052 would be 13 over 250. All right, now we get to the interesting ones. Non-terminating, so they don't stop, they don't have an end, but they repeat. So non-terminating, repeating decimals. So these are decimals that go on forever, but they're repeating forever. And so we can turn these into fractions, and here's how we do it. So we're going to go ahead and use algebra to prove that these are fractions. First thing I'm going to say is x is equal to 0.1 repeating. Okay, so that's what x is. Now, if x is equal to 0.1 repeating, if I multiply both sides of these equations by 10, I would get a new equation of 10x equals, and remember when you multiply by 10, you're just moving the decimal over, so I'd get 1.1 repeating. Okay, so I've got two equations there. Now over here, I can say 10x minus x, so this minus this would equal what? Well, 10x is 1.1 repeating, so I do 1.1 repeating, that's 10x, minus x, which is 0.1 repeating. And so on this side of the equation, we get 9x, because 10x minus x. On this side, the 0.1 repeating over here and the 0.1 repeating over here, since we're subtracting it, all of these ones that are repeating over here are canceling out all of these ones that are repeating over here. So 1.1 repeating minus 0.1 repeating, all these repeating ones cancel each other out because we're subtracting here. So we're just left with 1. Because all the 1, 1, 1, 1, 1, 1, 1 gets canceled out by all these 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1s. And now we can just divide by 9, and x equals 1/9. What was x? X was 0.1 repeating. So 0.1 repeating must also be 1/9. Tricky, tricky. All right, next one. All right, this one's a little bit more difficult because we have the 2,5 repeating. So this is basically 0.252525, and it just keeps on going. All the 2,5s just keep on repeating each other. We would start it the exact same way. We're going to say that x is equal to 0.25 repeating. And we can write that 10x, if we move the decimal over, we get something weird here. We get 2.525 repeating. Now, if I tried to subtract these two from each other, the 2.5 repeating and the 5.25 repeating, they don't match up, so I'm not canceling out the repeating portion. And that's really what we want to achieve with this second equation, is we want this repeating portion right up against the decimal place. And I don't have that. Because if I subtract these two, the 2.5 repeating is not going to cancel, and that's what I really want. So what I'm going to do is try 100x. If I've got 100x, I would get 25.25 repeating. And now the repeating portion is right up against this decimal place. And up here, I've got the repeating portion right up against the decimal place. So on this one, I'm not going to use this one because the repeating portion is not next to the decimal. So I'm going to say 100x minus x is equal to 25.25 repeating minus, because that's what 100x is, minus 0.25 repeating. And now when I subtract these, the 2.5 repeating is canceling out this 2.5 repeating, so all I'm going to be left with on this side is 25. Over on this side, I'm left with 99x. And so 99x is equal to 25. And I divide by 99 and get x is equal to 25 over 99. So that's what 0.25 repeating is. It's 25 over 99. Now, some of you might be looking at this and going, there's a pattern. All I have to do is, if it's in this place, put a 1 9. If it's in this place, I can put 2 9s and then just put 25 on top and I'm done. It doesn't always work that way. Next one. So again, this one is 0.1636, oops, not 66, 63, 63, 63, 63, so on and so forth. So we got the 63 repeating, but the 1's not repeating. So I'm going to start with x. X would be 0.163 repeating. 10x would be 1.63 repeating. All right, now this is what I want. I want the repeating portion right next to the decimal. I can't use this one up here because the repeating portion is over here in the hundredths place, not in the tenths place. I need to get the repeating portion right next to the decimal. So I don't want to use this one. This one's good. I've got the repeating portion right next to the decimal. So don't use this one because the repeating portion is not next to the decimal. So I'm going to do 100x. So that just moves the decimal over another one. So this would be 16.363 repeating. I can't use this one because the repeating portion is not next to the decimal. So I'm going to try 1,000. And I get 163.63 repeating. And I can use that one because the 63 repeating portion is right next to the decimal. So I'm going to use these two. So I'm going to do 1000x minus 10x is equal to 163.63 repeating minus 1.63 repeating. So if I've got 1000x minus 10x, that would be 990x. Over here, 163.63 repeating. The 63 repeatings cancel. So I get 163 minus 1, which is 162. All right, and then I'm going to divide both sides by 990. I get x is equal to 162 over 990. Now we can still reduce that fraction because I can tell it's going to reduce. They're both even. What else do I notice? 7, 8, 9. Oh, and 9 goes into both of them too. Okay, so 9 goes into both of them. Let's do that first. So 160, I can tell 9 goes into this one because if it's 1 plus 6 plus 2, that adds up to 9. So 9 must go into that number. So if I take 162 and divide by 9, that comes out to 18. So 9 goes into that 18 times, and 9 goes into this 110 times. Looks like we can still reduce it because they're both positive. So 2 goes into 18 9 times, and 2 goes into 110 55 times. So we got 9 over 55, and there's our answer. We've reduced it as much as possible. So 0.163 repeating is 9 over 55. So remember, you have to get the repeating portion right up against the decimal right here so that when you go over here, you can cancel out the repeating portions. Okay, next page. Square roots of perfect squares. All right, so we've talked about before, a square root is the opposite of squaring a number. Now, square roots of perfect squares are rational numbers because we can turn them into fractions. So perfect squares means this is a number multiplied by itself. So 4 is a number multiplied by itself. This is 2 times 2. So the square root of 4 is 2. And I can turn that into a fraction by just making that 2 over 1 because it's an integer. 16 is 4 times 4. So the square root of 16, since it's the opposite of squaring a number, this would be 4 over 1. Remember, if it says 16 in here, it's saying what number multiplied by itself is 16? Well, 4 multiplied by itself is 16. So what number multiplied by itself is 121? It's 11 times 11. So this would be 11 over 1, and now it's rational. 196, that would be 14 times 14, I think. Yeah. That's 14 over 1. There you go. So square roots are rational if and only if they're perfect squares. Because we're going to find out later on, non-perfect squares are not rational, they're irrational. And so we're down to irrational numbers. Irrational numbers are numbers that can't be turned into fractions at all. So it's impossible to turn these numbers into fractions. Now they do show up on a number line somewhere, but they can't be turned into fractions. The first reason why they might not be turned into, well, every single one of these can't be turned into a fraction because it's a non-terminating, non-repeating decimal, which means the number goes forever. And you, of course, have seen, these numbers before. Pi is a very famous non-repeating, non-terminating decimal. we know that pi is 3.1415, what is it, 92 something, 6, 5? Oh no, I'm running out of steam here. I think I've gone as far as I can remember. Anyways, this number keeps on going and never repeats itself. Now, there is a reason why we use this symbol. Because if I want that number written down, it's impossible to write down the number. So as you go through math, you're going to see a lot of symbols popping up. And the symbols represent numbers that are impossible to write down exactly. So a lot of times you've said in the past, oh, pi, it's 3.14. Well, no, not really. It's 3.14159265, and it keeps on going. It's impossible to write the number down. So a lot of times we just leave the pi symbol to represent this number because it's impossible to write that number down. And that gets us to radicals of non-perfect squares. So 74 is not a perfect square. If we wanted to pull out our calculator and find out what 74 was, the square root of 74, on my calculator, it says that it's 8.600232526.7. Now, my calculator is rounding because it's impossible to actually write down that number. The square root of 74 actually goes forever, and it never repeats itself. It's like pi. So the square root of 74, the best way to write that number is just to leave it like this and see we're using this symbol. If we're using symbols, that means it's impossible to actually write down the number because it just goes forever. So this is 8.6-ish, 8.60-ish. So we use the little wavy lines to show that that's not the exact number, that's just an approximation of it because it's impossible to write this number down. It's like pi. And remember, anytime we can't write down the number, we use a symbol to show what that number actually is. So pi, can't write it down, so we use the symbol instead. Square root of 74, impossible to write down, that's why we use the square root symbol, to show the number that we can't write down. Whew. All right, so how do we approximate radicals? And we're going to use a method to approximate them to the nearest tenth. There's other methods where we can approximate them to be more specific. We're just going to do a really basic one here. This is not going to be completely exact. We're just going for a general way that we can say, oh, it's about this much. So on this one, we've got the square root of 8. Now, the first thing I want you to think of when you are approximating a radical is what perfect squares does 8 lie between? Now, our perfect squares would be 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25, 36, 49, 64, 81, 100, 100, 121, 44, 169, so on and so forth. Okay, so those are all of our perfect squares. So what perfect squares is root 8 between? What's between 4 and 9? So root 8 is between the square root of 4, which is 2, and the square root of 9, which is 3. So that's telling me that the square root of 8 is between 2 and 3. And it looks like it's closer to 9, 3, than it is to 2. So I'm going to say that this is approximately 2 point something. Because root 4 is 2, root 9 is 3, root 8 has to be between root 4 and root 9. So it's 2 point something. And now we're just going to figure out how we can find out. Oh, dude, I got to blow my nose just a second. Pause. All right, I'm back. So what we're going to do is we're going to look at the distance from 4 to 9. Okay, so we're going to look at the distance between the perfect squares. So the distance between those perfect squares is 9 minus 4. That's a distance of 5. Now root 8, how far along that distance has it gone? Well, it's from 8 to 4, or 4 going up to 8. That's a distance of 4. So this is the distance from the lowest perfect square. So this is 4 over 5. So what's that saying? It's saying that root 8 is about 4/5 of the distance from root 4 to root 9. Because to go from root 4 to root 9, that's a total distance of 5. And root 8 goes 4 of those 5 distances. Because we've got root 5, root 6, root 7, root 8. So there's 1, 2, 3, 4, 5 to get to 9, but we've only gone 1, 2, 3, 4 of the way over there. So we've gone about 4/5 of the distance, which is, if you take 5 going into 4, you would get 0.8. So we are 2.8 approximately for the square root of 8. Now, is that going to always be really exact? No, we're just approximating. These distances aren't actually the same amounts. Like root 4 to root 5 is not the same distance as root 5 to root 6. It's just not, because this is not really linear here that we're looking at. So we're just making approximations. So this is a good way to approximate, but it's not going to be very exact. So if you just take out your calculator and you plug in the square root of 8, you're not going to get 2.8. You're going to get close to it, 2.828. So yeah, it's pretty close, but you're not going to get exactly 2.8 because we're just approximating. And this is not a perfect method for approximations, okay? So don't think that this is like the best way to find your radicals. We're just trying to approximate them and get a good idea of what these radicals actually mean. So the square root of 8 is about 2.8. All right, let's do our last one, square root of 60. So I can see here that 60 is between the perfect squares of 49 and 64. So 49 down here, 64 over here. So that's between 7 and 8, because the square root of 49 is 7, square root of 64 is 8. So root 60 is approximately going to be 7 point something, and we want to find out what that point something is. Now, if I'm going from 49 to 64, remember we're going to do the distance between the perfect squares. So we're going to say 64 minus 49. That's the total distance between these two perfect squares. And now we want to see how far along that path is root 60. So how far away is 60 from 49? So we're going to do 60 minus 49. So 60 minus 49 ends up being 11. 64 minus 49 ends up being 15. So we are 11/15 of the way across that path. So we would just say, okay, how many times does 15 go into 11? I don't know. Let's find out. So let's see. 15 goes into there. What's that? 105. So 7. 0.7. This is 105. Let's see if we need to round up, if we need to keep it at 0.7 or not. So we get 50. Yeah, this is going to work. It's 0.73-ish or so. So we're going to get about 0.7. If this would have said 0.78, I'd round it up to like 0.8 or something like that. So it looks like 0.77 is going to be my answer, because 11/15 is about 0.73-ish. So I'm going to say, okay, 7/10 of the way is about how much we made. Now, this is not going to be exact again. So, and we got to be okay with that because we're just estimating. So if I've got the square root of 60, (7.74). See, it's not 7.73. This is just an estimation over here. So we're close, not exact, but close. All right, that's all I got for you. We will move on to operations with square roots next time. See you later. Bye-bye.